Hello, everyone. Today we're going to look at example 5 from chapter 13b, which is looking at the complementary relationship between sine and cos. And we've actually been using this relationship a little bit already with our exact value triangles. So some of you might, just if you think about the exact values of sine 30, sine 60, cos 30, cos 60, you might remember that, hey, sine 30 is a half, cos 60 is a half, cos 30 is root 3 on 2, sine 60 is root 3 on 2. So there's a little bit of swapping going back and forth between sine and cos in sort of like an opposite fashion or in a complementary fashion. So we're going to look at this a little bit more. I think one of the nice ways to look at this is with our graphs. This can also be done with a unit circle as well. So if you don't particularly love the graph, feel free to ask me in class and kind of go through this explanation with a unit circle instead. With the graphs, however, we can see we've got these two beautiful sine and cos waves, and they look really, really similar in terms of the pattern. In fact, they're actually identical. One of the things that we can say is that cos and sine, depending on which one you're looking at, is 90 degrees out of phase. So they're 90 degrees out of phase with each other. In other words, sine is 90 degrees out of phase with cos, and cos is 90 degrees out of phase with sine. And by phase, I'm referring to like phase shifting. Now, we'll look a little bit more at this idea of a phase shift when we look at trig graphing. However, for now, just understand if I add things to my angle here, if I add something like pi divided by 2, I'm going to change the phase. I'm going to shift my graph to the left or to the right, depending on if I'm adding or I'm subtracting. So let's first look at this idea. I say that 90 degrees out of phase, which means, and I kind of already did it, but if I do pi divided by 2 and I subtract pi over 2 from x, what I get is a sine graph. In other words, cos is 90 degrees out of phase with sine, and I need to move that towards the right-hand side. Again, if I toggle my cos graph on and off, you can see now they perfectly overlap. What this means is I can say that cos of pi on 2 minus theta or minus x is equal to sine. And that's kind of one of the identities we need to remember. And I'll kind of put this up on a sheet at the very end. So cos pi on 2 minus x is equal to sine of x. Or cos pi on 2 minus theta is equal to sine theta if I change that value to theta. If I look at this kind of going the other way, if I make this back to just cos x, if I look at this the other way around, well, I can say the same thing is going to be true for sine. If I do pi on 2 minus x, I now see that pi on 2 minus x is also equal to cos of x. So if I have pi on 2, or if I have 90 degrees, and I subtract that from the angle, I get my opposite trig ratio. If we think of this in terms of our exact values, if I do pi on 2 or 90 degrees minus 30, I get 60. So if I have cos 30 is going to be equal to sine 60 based on this logic, which we know is true from our exact values. Equally, if I kind of flip this back the other way around, if I have pi divided by 2 and I subtract that from my angle, if I have sine 30, if this theta angle here is 30 degrees, say, for example, then if sine is 30, then sine 30 should equal cos of 90 minus 30, which is cos 60. Again, if we think of our exact values, sine 30 is a half, cos 60 is also a half. So I know this is true, at least for our first quadrant values, which brings us to this rule here. Sine pi on 2 minus theta equals cos theta, and cos pi on 2 minus theta equals sine theta. So these relationships here operate in quadrant 1. If we come over here to this picture that I've drawn, you can see I've got these 2 points, and I feel like it's good to conceptualize this both with the graph, but also with the unit circle. So I know, and we've kind of done this diagram a few times, if I take this length down here, we've looked at this length here being x, this length here being y. We typically get the coordinates for this point being x comma y. And you've seen me do it a few times now where I've said, hey, this can also be equal to, x is also equal to cos theta, y is also equal to sine theta. So we can write it as, let's just do it in green as well. We can write this as cos theta comma sine theta. That could be the coordinates of this particular green point we've got here. Now, theta in this case is going to refer to my angle over here. Now, the complement of this means that instead I have my angle from the y-axis. It's kind of like the opposite, as I keep bumping my home button, apologies. So the complement of this being this purple line is going to be given by this angle inside here. And what you might be able to see visually, obviously these aren't drawn exact, but because it's the complement, this length looks very, very similar to this length here. And in fact, they should be exactly the same. One of the ways to write my angle here for my purple line is I can actually write this as being 90 degrees. Let me write 90 degrees as pi on 2 if we're using radians. This whole angle could be thought of as pi on 2 minus theta, where theta is this angle inside here. So this line, my purple line, has the angle pi on 2 minus theta. My green line has the angle of theta. Now, I know if I do pi on 2 minus theta, I get the complement of sine, or I get the complement of cos. So I could write this dot point here as being, if it's cos theta, comma sine theta, and theta is pi on 2 minus theta, I could write this as cos pi on 2 minus theta, comma sine of pi on 2 minus theta. Now, this is kind of where this idea gets a little bit more interesting. I know from those values I got before, if I come over here, that sine of pi on 2 minus theta is actually equal to cos, and cos of pi on 2 minus theta is actually equal to sine, which means I could rewrite this particular coordinate point as being, because I think of this coordinate point as being sine theta, comma, cos theta. So again, complement you can kind of think of as being opposite. I'll put this in brackets as well to make it the same. So if I have the complement, you can see that my sine and cos are essentially swapping spots. Now, how this looks with an example, if we come across down here to the first example, or the first part of our example, if I have sine of pi on 2 minus alpha, I know that cos alpha equals 0.8, then part A is going to be equal to sine, let's make that all line up. Part A is going to be equal to sine pi on 2 minus alpha. I know from my identities that is going to be equal to cos alpha, which is going to equal 0.8. Now, like I said, this is it for quadrant 1. Now, there is a second set, which we can see over here. And again, we know we have trig ratios that exist in all quadrants. So let's have a look at what happens in quadrant 2. So in quadrant 2, I'm going to have a similar idea here, where I'm going to have this particular point. Now, the difference this time is, again, it's the complement. So I'm taking my angle from the y-axis. The difference here is that this time, this angle, let's just do this theta part in red. This angle, this theta here, if I do the whole thing from my horizontal x-axis from the positive quadrant, like I always do when I calculate the total angle of anything. If you look at this angle here, this is now going to be pi on 2 plus theta. That's sort of my big difference here, that to describe this whole angle, it's now pi on 2 plus theta. So the two complementary angles are pi on 2 minus theta and pi on 2 plus theta, but when it's pi on 2 plus theta, I'm in quadrant 2. When it's pi on 2 minus theta, I'm in quadrant 1. So let's have a quick look at what that looks like here if I did this as points. Again, I have cos theta, sine theta. It's just this time, instead of it being positive cos, because it's in quadrant 2 where only sine's positive, it's now going to be negative cos theta, sine theta, because it's in quadrant 2. So that does affect things just slightly. So if I still have the same idea that cos theta is equal to sine theta, it now means that this is going to be equal to, if I do it in terms of my ratios, or I should have written this, sorry, apologies. I should have written this as being theta. I can rewrite this as now being negative sine theta, comma, cos theta. And the cos theta part is going to stay exactly the same because, again, sine is positive in quadrant 2. So let's just quickly throw this back to the graph to see how this fits in. So if we come back here to my graph to help further illustrate this point, if I have pi on 2, if I have pi on 2 and I plus that with x, you can see now my sine function looks exactly the same as my cos function because these are my complementary relationships. If I do the same thing the other way though, if I do pi on 2 plus x, you can see now they look the exact same, but it's like one is flipped upside down. And that's because if we remember our value, cos of pi on 2 plus x actually is equal to negative sine theta because it's in quadrant 2. If I put a negative there, you can see now they completely match. So it matches with our graphs. It kind of makes sense based on the unit circle of when I'm plussing and when I'm minusing. And the key idea here, again, is going to be these two values, which is this relationship here, which is sine pi on 2 plus theta equals cos, and cos of pi on 2 plus theta equals negative sine. So they're the four things you have to remember. Really, all we need to know is just these four rules. However, it's good to kind of know where they come from, how they work. That's kind of what our unit circle and our graph helps us to kind of picture or understand. Let's just finish this off with an example of what this looks like. If I do part B, that is going to be cos pi on 2 plus theta. I know cos pi on 2 plus theta equals negative sine theta. Sine theta in this question over here is equal to 0.4. So that's going to equal negative 0.4. So that's really the whole idea, is just remembering these four values. To do part C is sine of negative theta. If my angle is negative, I'm going clockwise, which means I'm in quadrant 4, which means I can simply rewrite sine of negative theta like so, which is going to give me my answer here, the exact same as it was in part B. So thank you guys for watching. Hopefully all of that made sense. Any questions about that? Like I said, we can run through those in class.